Okay, today for this talk, we're joined with Dr. Bai, that leads the Advanced Materials and Manufacturing for Extreme Environment Laboratory at University of Nebraska in Lincoln. His lab aims to develop advanced materials that could withstand extreme environments such as high temperatures, irradiations, and corrosive gas and liquids. In next generation nuclear energy, petroleum, and aeronautic systems. Also develops novel advanced manufacturing processes for these materials and reveal the fundamental mechanics in manufacturing processes. His work has appeared in top journals such as Acta Material, Journal of American Ceramic Society. And today he will be talking about application of laser peening to ceramic materials. Welcome, Dr. Bai. Please, the floor is yours.
Thank you a lot for introduction. Hello, everyone. My presentation today is about the new topic of the LaserShock peening on ceramic materials. This is a research area we started from the 2016, funded by the National Science Foundation. And through the last 5 years, we have collaborated with my colleague, Professor Rongfeng Lu, he's a laser expert, and my colleague, Mike Nastasi. We have worked in this area for a long time and did a lot of work and efforts to apply the LaserShock peening to improve the mechanical performance of ceramic materials. Okay, so my presentation, first I want to have a brief introduction, and then I want to highlight the two parts is room temperature LaserShock peening on silicon carbide, and our recent high temperature LaserShock peening on sapphire single crystal alumina. Why we are interested in this is because the motivation for this work is all the ceramics has low fracture toughness. Also, the ceramics has a much higher strength and corrosion resistance than metals in extreme environments such as high temperature. Their low toughness is a big limit for ceramics for all the industry applications. To address this issue, first, the ceramics has low toughness because they have a low plasticity at room temperature. This can result in the crack sensitivity, and which is makes ceramic very brittle and easy to break. So our concept here is we wish to use the LaserShock peening to induce the localized plasticity into the ceramic materials to improve their mechanical property, which I will explain this more about the concept. Our research goal is to understand the fundamental mechanism during the LaserShock peening of the ceramic materials. I would like to say we are one of compared to the metal, the LaserShock peening is not widely applied to ceramic. So we are doing some pioneering work in this area and trying to understand their scientific mechanism. I will skip these slides, but because I already many speakers already talked about the LaserShock peening, but I would like to highlight something here. Is like one is Shockwave has very high pressure, several gigapascal high pressure, and also the plus deformation here is a very high strain rate. This will be something important for the mechanism. At Nebraska, our lab developed our own LaserShock peening system. This is an experiment. This is a lab size system. So we use an ND-Young laser with nanosecond pulse duration, and we have our setup here for peening of the sample on the three-dimensional stage. So we control the scanning of the laser beam for the LaserShock peening of the large area, or even some curved surface. The hypothesis here is the compressive radial stress generated by LaserShock peening can improve the cracking resistance of ceramics because they can inhibit the crack propagation on the surface. This is actually motivated by some work in the ceramic before, which is generate a surface compression, like using the short peening, using the thermal quenching or other similar process. Those a lot of research have reported that if we put this surface compression, This can generate, this can improve the fracture resistance, wear resistance, and have many benefits for ceramic. But compared to those previous literature, the reason we use LaserShock peening is because the advantage to generate a much deeper compressive radial stress, which can be 1 millimeter or higher. And by using the laser to control the system, we have a higher speed, easy control, and no contamination. So far, we have listed here some ceramic system we already found to be successful for LaserShock peening, which including the alpha alumina, silicon carbide, silicon nitride, zirconia. First, in the second part, I would like to talk about our work on using the room temperature LaserShock peening on the silicon carbide ceramic. The sample we got is some polycrystal ceramic from a commercial vendor, and when we got these samples, we do analysis, and we found the sample is not pure. It has some silicon phase along the grain boundary. Later, we talk about this the rule of the silicon phase. This is actually have some benefit, which is unexpected. But we conduct LaserShock peening in the following condition. Here, this is optimized condition. What we found here is pulse energy is a very important parameter to control the surface morphology and the damage. If the pulse energy is too low, then the peening effect is also very low. But if we use a very high pulse energy, then it can generate a large number of the cracking on the surface, which is give us the negative effect. So there is an intermediate energy, and in this case, we found 600 mJ is the best pulse energy for silicon carbide. And here shows surface morphology of the sample before LaserShock peening, after LaserShock peening. With this energy, we only see very tiny and very few micro crack. Most of them are from the pre-existing flaws. And the surprising result here is similar to the metal. We do the TEM analysis of the cross section. We found that near the surface and grain boundary, there's a significant amount of the dislocation. So here shows the left shows a cross section TEM image. This is a weak beam dark field imaging, and you can see a high density of dislocation near the surface. And the picture on the right also shows a dislocation occurs even at a depth of 6 micrometer and near some grain boundary. So all these results are surprising because what we are doing here is a LaserShock peening at room temperature, and the common knowledge is a ceramic is very difficult to activate dislocation sleep at room temperature. So we call this is a localized plasticity in ceramic because the plus deformation of the dislocations is localized near the surface and grain boundary. And this is not only on the silicon carbide, this also occurs in alumina. So we published 2 different papers in here. So this seems to a common feature. And to explain this unusual phenomena by the LaserShock peening, we go back to check some literature a very long time ago. And what we found here is one thing is when the shock wave generated by LaserShock peening propagate across interface, it can enhance the shock wave because some shock wave reflected back, and the shock wave prior at the interface is enhanced when the different materials have the different acoustic impedance. And this kind of phenomenon is used for us to explain here, because in our case, the shock wave will transfer from the vinyl coating to the ceramic. So near their interface, there could be some enhancement of shock wave. And in the second case, our grain boundary of the silicon carbide contains some silicon phase. So their acoustic impedance mismatch between the silicon carbide and silicon also can generate some local enhancement of shock wave. So in general, we think that those this shockwave, high shockwave pressure, together with the ultra high strain rate, because laser pulse duration is very short, just a nanosecond. So combine those, I think this can generate some localized pulse deformation ceramic. I would say this is still a preliminary theory, and I hope some modeling can help us to explain the mechanism. But no matter the mechanism, the result is clear. We use X-ray diffraction to measure the radial stress along the depths. We see that the silicon carbide has generated a very high compressed radial stress on the surface, and which is can extend to a depth of 800 micrometer. Because of the compressed radial stress, this can enhance the mechanical property. Because the laser shock peening is a surface effect, so for evaluation of the mechanical property, we think the Vickers indentation or the nano indentation would be a better method to study than the microscale method and the SEN, such as SENB. So in the ceramics, the perhaps knowledge is that if you make a Vickers indentation, and because ceramics is brittle on the edge, it will generate some crack. And the crack lengths can be used to put into the equation to calculate the fracture toughness. So in here, we compare the case before the laser shock peening and after laser shock peening. Can see the crack length is significantly reduced, which indicate the fracture toughness is enhanced. And we can quantify the results here. The fracture toughness is measured this way, and the bending strength is measured by using the traditional 3-point bending test, in which we do the laser shock peening on the whole surface of the bending bar. And we found that both fracture toughness and the bending strength is significantly increased in the silicon carbide after laser shock peening. The explanation, basic explanation for those mechanical property improvement is I would like to use the example by Callistis in his paper. So if you consider the case without any compressed radial stress under the tensile load, the straight crack will propagate quickly in ceramic because ceramics are very brittle. But if we have built-in compressed radial stress, those can reduce stress intensity factor and the crack tip. And also, because compressed radial stress, it will increase the threshold for the critical stress for crack propagation. And this effect can be quantified if we use another model by the David Green, famous ceramic scientist. So here, his model shows if you have straight crack in ceramic materials and you have a compressed radial stress field, the stress intensity factor can be significantly decreased. So this is used by us to explain why the fracture toughness is and the tensile, the bending strength is enhanced after laser shock peening. The last part of my presentation, I would like to talk about our novel work using the high temperature laser shock peening process. This is a new concept because the motivation is here. When we do the laser shock peening at room temperature on ceramic materials, because ceramic is very brittle, we need to have very careful control of the laser parameter to avoid the shockwave damage. So in 2016, we developed this new concept to perform this new idea to perform the laser shock peening at high temperature, because we know the ceramic can have a higher dislocation activity at high temperature, and a lot of ceramic has the brittle to ductile transition. For example, alumina, the transition temperature is about 1000 C. So above the transition temperature, ceramic shows much more plasticity and ductility. And also because of the higher ductility at high temperature, the surface damage by the shock wave can be also much reduced. And so this is idea, but when we perform the work, we found the key challenge is about the system. because we cannot now we cannot use water, we cannot as a plasma confining media, we cannot use those the setup we use for room temperature. So we have spent a lot of efforts to make selection of the materials suitable for high temperature for the sacrificial layer, plasma confining layer, the heating source. So finally, we invite our prototype system and file a patent. And here shows a diagram of our experiments. We use the stainless steel coating as a sacrificial layer. And we use finally we choose fused silicon as a good material for plasma confining media. And here I would like to talk about some work we did on the single crystal alumina sapphire. And recently, we also have been successful in the silicon carbide polycrystal ceramics using the high temperature laser shock peening process. So why we do sapphire is here. I show the reasons like this. In the beginning, we do the laser shock peening at room temperature. We found that even with any change of with the optimization of the parameters, the laser shock peening at room temperature for the sapphire is never work. You can see here the SEM image. The surface always generate a lot of micro crack, and also even some some materials drop or pull out by laser shock peening. But when we raise the temperature to 1200 C, we found the shockwave damage now is minimized. We only see a very few micro cracks. So it's the high temperature laser shock peening significantly decrease the surface damage. This is also true for silicon carbide. So for the measurement of residual stress here, we choose Raman instead of X-ray because we found the Raman spectrum has a much higher resolution. It can, in our system, we can have a resolution as low as 20 micrometer. So we can now measure the compressed residual stress distribution in one laser shock peening spot. And the mechanism to measure the compressed residual stress by Raman is by the Raman peak shift. There's already some literature about this, and there's established equation about the Raman peak shift with residual stress. And here you can see after laser shock peening, the main peak shift has a blue shift, which indicates some compressed residual stress. And then also we can use those equations to quantify the results. And here, this is a laser shock peening spot, and we do the lens scan of the Raman measurement. You can see in the middle of the spots, there is a significant 1 gigapascal compressed residual stress, which decrease when away from the center. On the edge, you can also see some tensile stress, which is to balance the compressive stress in the center. But anyway, we found in sapphire it can generate a very high compressive residual stress.
2 more minutes.
Okay, for the microstructure here shows a cross-section microstructure analysis by the TEM, and before the high temperature laser shock peening, there's no dislocation, and after laser shock peening, you can see here we generate a very high density of dislocation, and the dislocation density decrease with the depths, but you can still see a lot of dislocation. And by analysis of Brooks vector and the slip plan, we found that most of them are base plan dislocation. So base plan dislocation is consistent with the deformation mechanism of a single crystal sapphire, which is in which the main slip system is a base plan at high temperature for alumina. We think the dislocation here is activated by the laser-driven shock wave. One evidence here is the shock wave decrease with depths, and the dislocation density also decrease with depths. After the high temperature laser shock peening, when we study their mechanical property by both the Baker's indentation and the nano indentation, we found the crack length is significantly reduced, which indicate fracture toughness increase. And here, the table here shows the the measurement of the nano hardness, micro hardness, and fracture toughness, you can see all of them has significant increase. And again, the mechanism for this is because high compressed reduced stress to reduce the stress intensity factor of the crack tip. Because sapphire is a very good optical ceramic, it has a very high optical transformation in a large range of the wavelengths. So we are curious if the LaserShock peening has some effect on the optical transformation. But the results here shows it's very good. It's only have slight reduction. So the optical transformation is maintained. So this is suggests there could be some promising application of our process in optical ceramics in other ceramic system beyond the sapphire. So in summary, we found the LaserShock peening can activate the localized plot deformation in ceramic near the surface at a different temperature. And the mechanism could be related to the very high shockwave pressure and other high strain rate deformation. And we have invented our novel high temperature LaserShock peening process, which seems to be more effective by room temperature LaserShock peening to decrease shockwave damage and enhance dislocation activity. And in the ceramics, similar to the metal, we can also generate a high compressed reduced stress. And the fracture toughness, strength, and hardness can be enhanced by LaserShock peening. And below I show some list of some our publication and patent. If you're interested, you can get some more details of our work from these publications. So finally, I would like to acknowledge the funding support from NSF for 2 awards, and also my students and my collaborator of Professor Runfeng Lu's group, Amanda Cross from University of Florida, Michael Nastasi from Texas A&M, and also many people in the field of laser and ceramics who gave me a lot of support and suggestions. And here's what we are. We are where we are. We are in the middle of US, and we really like some collaboration and discussion. Thank you very much.
Thank you, Dr. Bai.